Okay, thank you for coming to this talk. My name is Erion Plaku, and this is joint work with my PhD student, Duong, who is here in the audience. So this talk today is about cooperative multi-robot sampling-based motion planning with dynamics. So here's a movie of a solution obtained by our planner for a fairly complicated instance. Here you have 10 car-like robots, and their objective is to go to the different goals that are marked. So robot 2 in there needs to go to goal 2, robot 1 needs to go to goal 1, and so on. And the motions that you see in here, they are all dynamically feasible, and they also need to avoid collisions with the obstacles and each other. There's no explicit coordination in the framework. It just comes about as a result of the search algorithm that is used underneath to compute these collision-free and dynamically feasible solutions. So what makes this problem quite challenging in the setting considered here are the underlying robot dynamics. The robot dynamics express the relations between the controls that you apply to the physical systems, the underlying differential constraints that they may have, and the new state or the resulting motions that come as a result of applying those controls. So from an abstract perspective, you can think of those as being described by some set of differential equations. Here are some differential equations describing the motions of a second-order car model. From an abstract point of view, you can think as having a dynamic simulator. You pass to it the current state, the current control input, and the small time step, delta t, and this dynamic simulator gives you the new state. And then you can have your collision checker to detect whether or not this state is valid, and then you either accept or reject the state based on whether or not it is in collision with the obstacles or other robots. Now, why are dynamics important? When you are dealing with these physical systems, if you do not take dynamics into account, then your plans might not be feasible. Think about the simplest example where you have a car, you are planning, let's say, in a discrete space, and you are making the car move sideways, but it cannot because of the underlying dynamics. So it is quite important to take the dynamics into account. If you do that, though, you run into search issues because now you are dealing with an infinite space that has infinite breadth, but also the solution trajectories. If you are thinking of going from a start state to the goal state, you need to apply many different controls in succession. So you do have the two classical problems in search, both breadth and depth. So in order to handle those things efficiently, what do? There are also instances where we need cooperation among the robots, and this cooperation, as I said, is not computed explicitly, but it needs to come about because of the environment in which the robots are operating. So here, these robots, robot 0 needs to go to goal 0, but robot 1 and robot 2 are on their prevent robot 0 from going to that location, so they have to make way for robot 0, and similarly robot 2 has to get out of the way in order to get to allow robot 0 to go to its location. And the other challenge that comes about is the high dimensionality. As you add more and more robots, your state space increases. Each of these robots has about 5 or 6 variables, so adding more robots increases the dimensionality of the state space. And when we talk about motion planning problems, when you deal with dynamics, this 50 dimensions is very, very large. We usually can do about 10 or so dimensions, and going to 50 or so, it's quite a lot. So in terms of related work, we have seen multi-agent path finding, which focuses more on discrete aspects, focusing more on how do you do it over graphs, regular grids, or grids with some sort of structures, as we saw in the previous talk and many other talks in this conference and other conferences. From the robotics perspective, we have focused mostly on the continuous state space, where you do take into account the geometry of the robot, the physical shape of the robot, and motions in the configuration space, mostly ignoring the dynamics, but just think about it, translations and rotations. And there the approaches can be categorized very similarly to the approaches in the discrete world. So we do have the centralized approaches when you have multiple robots, but you just treat that as one system. So there there the dimensionality increases, and that becomes the bottleneck for decentralized approaches. On the other hand, they can provide guarantees, and in many cases we focus on what is known as probabilistic completeness, so algorithms such as probabilistic roadmap or rapidly exploring random trees and many other sampling-based motion planners can be applied in this centralized framework. It's just that the runtime will increase rapidly as you increase the dimensionality, as you increase the number of robots. For that reason, people also looked at decoupled approaches. In decoupled approaches, you do planning one robot at a time, and when you plan the path for one robot, you completely ignore the other robots. Then what happens when conflict arise? You may be trying to do velocity tuning, essentially slow down the robots or make them move faster to avoid those local conflicts, or come up with some other strategies to avoid local conflicts. The problem with these approaches is that they lose that probabilistic completeness guarantee, so they now become incomplete, and it is difficult to solve problems like this one where robots have to change places and they block each other. And the other component, the other category is prioritized approaches, where you plan, again, the paths one at a time, but when you plan the path for the ith robot, you consider the paths for robots 0 to I-1 as moving obstacles, so you try to avoid those paths. So prioritized planning tends to be better than decoupled approaches, but still runs into the same issues. It's still incomplete because it may not be possible to assign priorities that will always guarantee a solution. So the proposed framework in this talk is to, in order to deal with robot dynamics, we are going to expand the motion tree. So in this way, we avoid what are known as boundary value problems. And in order to guarantee probabilistic completeness, the motion tree is going to be expanded over the composite state space. But in order to make this expansion efficient, we are going to use a discrete layer, a simplified layer, that is going to guide this motion tree expansion. So the discrete abstraction is going to come from probabilistic roadmaps, and it's going to rely on standard multi-agent path-finding algorithms to provide general guides of how you need to expand the motion tree in the continuous state space. So just quickly, a little bit of background about sampling-based motion planning. This is a general framework. I'll try to present this in the context of a search tree. So here, there's a state X, and you apply different controls. So those are the means of how you can generate successor states. So this is the parent, these are the sum of the children, but you can imagine that by applying different controls, you can generate infinitely many successor states, but that's the mechanism of how you expand the search tree. And after that, you can think of your search algorithms from the discrete world and apply them in a continuous setting. So start from a state, select it, apply the successor function, repeat this process, and so on until you eventually reach the goal. The efficiency of these algorithms depend on how you guide the search, what kind of methods do you use to guide the search effectively. This is the framework for the schema for the proposed approach. I want you to focus a little bit in here. This is the discrete abstraction layer, which is a graph. It's a composite roadmap, and this roadmap is passed with multi-agent pathfinding to find paths that ignore the underlying dynamics of the vehicle. So just focus on this discrete abstraction. These paths now serve as guides to expand this motion tree that is expanded in the continuous state space, taking into account the underlying dynamics of the vehicles. The motion tree is partitioned in what are referred to as equivalence classes. These are equivalence classes capture the same discrete information that comes from the roadmap decomposition. And this process is repeated. There is this loop in here where you expand the motion tree for a little bit, and then you query your multi-agent pathfinding to find a guide, expand, repeat, and change the costs as well in order to avoid conflicts that may arise. And now some more technical details. So this is a roadmap that is constructed by doing sampling-based PRM, probabilistic roadmap. So you sample a bunch of configurations, check which ones are in collision, ignore those, keep the ones that are not in collision, and connect neighboring configurations with collision-free paths. This gives rise to a graph. You have vertices, edges, and costs. Costs are based on the distance between the two configurations, but also the clearance, how far that configuration is from the obstacles, because we want to promote generations of paths that do not get very close to the obstacles, because those paths will be harder to follow. So we would like to maximize or at least increase the clearance from the obstacles. But from the perspective of multi-agent path finding, now you do have a graph, and you can use pretty much any multi-agent path finding algorithms to find paths for these multiple robots. We can construct one roadmap for every robot that we have, but if robots share the same physical shape and the same configuration configuration space, then you can construct just one roadmap. But when you do the multi-agent path finding, you are computing that explicit graph, the roadmap decomposition of all the graphs. So this is the graph R1 times Rn, over which the multi-agent pathfinding algorithm is operating. And again, this graph does not need to be computed explicitly. It is computed implicitly on the fly, so you can generate the successors based on your current graph vertices. So let's suppose that you have this robot 1 in here, robot 2, and robot 3. They need to go to some particular goals. You call your multi-agent pathfinding algorithms, and let's say it comes up with this path. So these paths now will serve as guides for the motion tree planner to expand the motion tree. So suppose these are the paths, and then the idea is to expand the motion tree along these paths. And when robots come close to one another, we would like to avoid conflict. So what happens in those cases, new equivalence classes are created, and we come up with, we call again the multi-agent pathfinding algorithms, and it may come up now with alternative paths that the robots need to follow. And this process is repeated until eventually we do have a solution that allows the robots to reach their goals. There are some more technical details to make this work correctly and to make it work efficiently. One key component, as I said, is the partition of the motion tree into equivalence classes. And the idea there is to group together all the vertices that share the same discrete information that map to the same set of roadmap configurations. And you invoke multi-agent search from each equivalence class. And then preference is given to equivalence classes associated with low-cost roadmap paths, because those are more likely to expand and reach the goal configuration. So these are some experimental results. So this is the scene that I showed to you before. Our algorithm here is in this pink color. So as you can see, it scales very nicely with the robot. The runtime here is a logarithmic scale, so our algorithm takes about, when you consider 4 robots, it takes slightly more than 4 seconds. And if you compare to some state-of-the-art approaches, you can see that our algorithm does much better. These are prioritized versions of GUST, which is one of the fastest algorithms for doing robot motion planning, and RRT, which is one of the more popular algorithms, and then centralized version of RRT, which does not scale very well. And this is throughout many different scenes. This one is a more open scene where the prioritized approach tends to work quite well, because there aren't that many conflicts that arise. So that's why you see that the GUST here does better in terms of the runtime, because here there's not so much need for avoiding conflicts. You can use prioritized approaches to get good results. But when you have complex scenes like this one in here as well, you may run into a lot of issues, so the prioritized approach here does not work very well, and our approach works quite well. And for these other scenes where cooperation is very necessary, you cannot solve the problem without having this cooperation. The other planners fail to find a solution in a reasonable amount of time, so only our method is able to solve these problems in a matter of 1 or 2 seconds. What is important coming to the discrete community is this graph in here, which shows a little bit the runtime distribution. The bar in blue refers to the multi-agent graph search. So throughout the execution, as we expand the motion tree, the multi-agent graph search is called about 100 times. So this is the total percentage that is spent by the multi-agent graph search. So as you can see, as the problem becomes more complex, a lot of time is taken by this multi-agent graph search. And that is actually a good thing, because what is happening is that the algorithm is shifting the burden from the expansion in the continuous space to using the discrete search as a guide. But nevertheless, there's a cost that is imposed by that multi-agent graph search. So what that allows us to do is that as you develop better algorithms for multi-agent graph search, we can incorporate those, and this will allow us to reduce the runtime and also to scale to a larger number of robots while taking the dynamics into account and the physical dimensions of the robot as we do these motion planning algorithms. So in conclusion, the takeaway message is that when you deal with these problems that are high dimensional, that have physical constraints coming from the underlying dynamics of the robots and their geometric shapes, one important component is to do the search in this hybrid space that consists of the continuous components, but also from this discrete abstraction that serves as a heuristic, as a guide for this search that happens in the continuous space. So if you have this interplay between the discrete and the continuous, you tend to improve the runtime efficiency and are able to solve problems that you could not solve with one approach alone. So that's all, and thank you for listening, and I'm now open to questions.
I have a couple of questions. The first one is, you didn't talk about probabilistic completeness.
Yeah.
Do you have any guarantees here
Yes.
on the algorithm? And the second is, which path planning algorithm did you use under the hood? And for the multi-agent, the discrete one.
For this one, it was WHCA star, the silver 2005 one. So just some standard one, not necessarily the fastest, but good enough. Yeah.
Heard you to use, I think M-star is probably very fit for this, right?
Yeah.
My default would be to look at CBS first.
Yeah. But the point is that any multi-agent algorithm, as long as it operates over graphs, would be compatible with this framework, and you can just plug out whatever we have and plug in whatever you'd like to use. And the better the multi-agent algorithm, the more efficient the overall approach is going to be. Yes?
So just on a related question, have you done comparisons with building a PRN for the respecting the robot dynamics than just writing your favorite?
You cannot build a roadmap that is going to respect the robot dynamics, because roadmaps require you to connect configuration or to connect states with one another, and when you have dynamics, you run into two-value boundary problems where the exact steering is not usually feasible, and if you use numerical approaches, you leave gaps in the edges. So that's one of the main reasons as to why when we deal with problems that have underlying dynamics, we expand the motion tree rather than building a roadmap.
So do you run into any issues with the sparsity of the PRM and the solvability of the multi-agent problem on that graph?
Yes, of course. If you make the roadmap very sparse, then your guides are going to suffer. So the question of how dense or how sparse the roadmap is going to be, it's quite important. So initially in here, we create a roadmap that's good enough sort of to connect and cover almost every part of the configuration space. But one thing that you could do is that if you see that a lot of conflicts are arising, then you can just sample some more in those areas and add more configurations. We haven't done it in this work, but it's a nice extension to think about, that you can dynamically adjust the roadmap size as you go along.
Okay, with that, I will let's have our next speaker and thank our